Hello everyone. In this video, we are going to explain how an AXI4-Lite read command works. The entire AXI4-Lite read protocol will be explained step by step. To make sure that the protocol is clear, we will design a complete custom IP block for it in Verilog. The IP block we will design is a ROM with pre-initialized contents. When the MicroBlaze processor issues an AXI4-Lite read command, the ROM returns the requested value. Before watching this video, I highly recommend watching the previous lesson. In that video, we explained how the AXI4-Lite write command works and went through an end-to-end example of designing custom IP. We also created the MicroBlaze block design that will be reused in this video. Because of that, this lesson will focus on the read command IP itself. We will not repeat the full block design setup, since that was already covered in the previous video. Alright, let's get started. When the processor issues an AXI4-Lite read command, data is returned from a register inside the custom IP block back to the processor. The read transaction uses two phases: read address phase and read data phase. The table below shows which signals are used in each phase and whether each signal is driven by the processor or the IP block. When the processor executes an AXI4-Lite read command to a custom Verilog module, the Verilog module uses the pink signals as inputs and the green signals as outputs. It does so by using the following rules. The animation shows exactly what happens during an AXI4-Lite read command. At time t0, the IP block already has AR ready high, meaning it is ready to accept a read address. At time t1, the processor drives AR address, AR prot, and AR valid. AR address contains the register address the processor wants to read from. AR prot is set to 0 for normal reads. AR valid tells the IP block that the processor has sent a valid read address. At time t2, AR valid and AR ready are both high at the clock edge, so the IP block saves AR address. After this point, AR address and AR prot are no longer relevant to this read transaction. The processor lowers AR valid and the IP block lowers AR ready. At time t3, the IP block uses the saved address to select the data that should be returned. It drives RData, RRESP, and RValid. RData contains the value being returned to the processor. RRESP is set to 0 for a normal successful read. RValid tells the processor that the read data is valid. At time t4, the processor drives RReady high. RReady tells the IP block that the processor is ready to accept the read data. At time t5, RValid and RReady are both high at the clock edge, so the processor accepts RData. The full AXI4-Lite read transaction is now complete. After this point, the IP block lowers RValid. The IP block returns to its initial conditions, which causes ARReady to go high again. As an example, we will design an IP block that implements read-only memory, a ROM. This IP block will act as the AXI slave that receives read commands from the processor and returns stored data. The ROM values will be written directly in Verilog, so the processor can read predefined values from inside the custom IP block. To test the design, we will package the Verilog module as a reusable Vivado IP block, connected to the MicroBlaze processor, and write software that reads the ROM contents and prints them to the serial terminal. If the serial terminal prints the stored ROM values during the live demonstration, that proves that the AXI4-Lite read slave is working. Alright, so this here is the Verilog code used to implement the custom AXI4-Lite ROM slave. On lines 1 to 38, the module parameters and ports are declared. The parameters define the AXI address width and the AXI data width. On lines 7 and 8, we declare the clock and reset. On lines 10 to 25, we declare the write bus. This video is focused on the read bus, so the write bus is not the main topic here. However, the write bus is included so that Vivado packages the module as a complete AXI4-Lite slave interface. This allows the block to connect cleanly to the MicroBlaze AXI interconnect without strange manual connections. On lines 27 to 37, we declare the read bus. The read bus is used by the processor to send a read command into the IP block and receive data back from it. On line 44, we declare the ROM. This line creates 8 memory locations, where each location stores 32 bits of data. On lines 46 to 52, we initialize the ROM contents. The loop makes address 0 store 0, address 1 store 1, address 2 store 2, and so on until address 7 stores 7. On lines 58 to 61, we define the 4 states. Each state corresponds to one of the 4 AXI4-Lite read rules. On lines 63 to 66, we define the internal registers used by the state machine. The register on line 63 stores the current state. The register on line 66 stores the address received from the processor. On lines 68 to 78, we implement the reset behavior. On lines 87 to 96, we implement Rule 1. This is the initial condition state. The IP block raises AR ready, clears R valid, clears R resp, clears R data, clears the saved read address, and then moves on to the address save state. On lines 103 to 110, we implement Rule 2. When AR valid and AR ready are both high, the IP block saves AR address, lowers AR ready, and moves to the return data state. On lines 118 to 135, we implement Rule 3. This is where the IP block uses the saved address to drive our data. For 32-bit AXI reads, the processor sends addresses that are multiples of 4. In other words, it sends addresses 0, 4, 8, 12, and so on. Because of this, we can convert the addresses into a normal ROM index by using bits 4 to bits 2 of the address. After the correct ROM value is selected, the module places it on R data, sets R resp to 0, raises R valid, and moves to the wait response state. On lines 142 to 148, we implement Rule 4. When R valid and R ready are both high, the processor has accepted the read data. The IP block then lowers R valued, clears R resp, and returns to the initial state. Finally, on lines 163 to 201, we implement a simple write placeholder. These lines accept write commands and return a normal response, but they ignore the written data. Before making the block diagram, you must store the Verilog file in a known directory. This is the directory that I am using for it. This here is the block diagram from the last video with the peripheral blocks removed. If we try to add the ROM IP block, you will see that it will not show up. To make it show up, we must package the IP. When packaging the IP, select the directory where you saved the Verilog file. Now we can add in the IP block for the ROM and UART. Also, we must change the AXI interconnect settings to support two masters, one for the ROM IP and one for the UART. After adding in the UART block, we must make its pins external. The names of the pins should be renamed to match the constraint file. This here is the constraint file used in this project. Then we must verify the design and automatically assign addresses to the peripheral blocks. After doing that, we can see the addresses in the address editor. The block diagram is now done, so we can generate an HDL wrapper. Then, export the hardware into a known directory. This will generate the XSA file that Vitis will use. This is the directory where I chose to have the XSA file be exported to. Then generate the bitstream. After the bitstream has been generated, program the device and then launch the Vitis IDE. Create an application project, then select the XSA file that you exported earlier. Give the project a name. Click Next, and then create a blank C project. Then create a new C file to run the main program in. Now copy and paste the provided code and build. This code is a simple program that makes the processor read all 8 locations from the ROM IP block and then transmit the read values over UART. After this build is finished, click on Run Configurations, click on System Project Debug, click on Target Setup, uncheck Program FPGA, then apply and run it. You can see it running on the bottom right. After it is finished running, open up the Vitis serial terminal. After the terminal has been opened, connect the FPGA to it. To do this, click the green button and configure the settings to match the settings that we chose for the UART block in the block design. After running the program, we can see that the correct values are printed. This proves that the ROM block, the MicroBlaze connection, and the Vitis code are all working correctly. Alright, so in the next video, we're going to design an IP block that supports both reads and writes. Before watching that video, I recommend you trying this problem yourself first. Then, after you attempt it, you can watch it in the next video to compare your solution. If you can complete this problem on your own, then that means that you understand the full AXI4-Lite protocol well enough to start building much more useful processor-controlled IP blocks. Alright, that's all for now. Looking forward to see you in the next one.